Good evening, everyone. First of all, thank you very much, Benny and the GWPF, for inviting me to give this talk. As you see, I've been giving this talk for about a year and a half now, since The Economist published this big front page, announcing the death of the internal combustion engine. So I started looking into this, and as you see, the title is it really the end of internal combustion engines and petroleum in transport? Well, let me answer it straight away. In my opinion, absolutely not, and I'll explain why this is so. There have been a couple of peer-reviewed papers published on this, and if anybody wants it, they can send me an email. My email address is there, kalghatgig@gmail.com. And I'll send you copies of the papers where there is a lot of detailed discussion and the correct references and so on. First, before we get into the nitty-gritty, let me just hold on. Let me just. Sorry, where did this go? Let me just give some introductory remarks. To put the whole thing in context. First of all, globally, transport accounts for about 14% of global greenhouse gases, including CO2, methane, and nitrous oxide, and so on, and about 20% of energy use and 23% of CO2. By the way, this 14% is the same percentage that livestock farming produces. So essentially, when people say they want to ban combustion engines, internal combustion engines for transport, you could very well say we should ban all, livestock farming, for instance. And the size of the problem is very large. Currently there are about 1.2 billion light-duty vehicles, that is cars and vans, for passenger transport, and over 350 million commercial vehicles. In the UK, there are around 32 million light-duty vehicles. Actually, light-duty vehicles only account for about 45%, 44 to 45% of global transport energy. So even if you converted all passenger cars into, take away the internal combustion engines from there, you will only have solved about 45% of the problem. I'll come to this issue later on. And transport is essentially driven by liquid fuels, at the moment, because they have become fuels of choice because of high energy density, ease of transport and storage, and therefore over the past century or so, very extensive infrastructure has grown around this. And it's very difficult to, it will be very challenging to replace this, by the way. Every day, the world uses about 4.9 billion liters every day of gasoline and diesel, gasoline and 4.9 billion liters of diesel, and 1.2 billion liters of jet fuel. That's about 11 billion liters of liquid fuel every day, okay? So the demand for transport energy is also growing, but mostly, almost entirely in non-OECD countries like China and India, basically, about 1% per year. And petroleum, there's oil and transport are extremely closely linked. 95% of the transport energy comes from petroleum-based liquid fuels, and 60% of all oil goes to make transport fuels. So these are the basic facts. Now, so hold on. There is and the second point, which is very interesting, actually. Sorry, where's why am I? Okay, sorry. Yeah, which is very interesting to remember because it has some relevance to what I say at the end of the talk, is the demand growth for transport energy is much greater for commercial transport because there is much more scope for improving the efficiency of light-duty vehicles for various reasons. I won't go into the details at the moment. And essentially what this means is in the future, as we go forward, more oil will have to be boiled to make more diesel and aviation fuel, essentially. And this will result in greater availability of low-octane gasoline-type fuels. which would normally have gone to make gasoline fuels, but the demand globally is decreasing. I mean, by the way, these trends are maybe different in different countries, but I'm talking about the global trend. And this trend has been recognized by the oil industry for a long time. So lots of investments are being made to make more diesel and jet fuel and so on, especially jet fuel. Jet fuel demand is increasing extremely fast in non-OECD countries. So this is important because we have to start using these low-octane gasoline components as well in transport in the bigger picture, and I'll come to that in the end. But the main headline is that most credible projections say that even by 2040, transport will be dominated by combustion engines. 85 to 90% of transport energy will come from combustion engines, and about all that energy will come from oil. So World Energy Council, US EIA, BP, ExxonMobil, OECD, not OECD, the oil and, various other oil companies also come to this conclusion. So it is imperative to improve such engines in order to improve the sustainability of transport. This is important to remember when I talk about battery electric vehicles and so on. Let's focus on the electrification of transport. Because this is, as everyone said, this is a topic of great interest, especially today. And yes, first of all, we have to remember there are different degrees of electrification. When we talk about eliminating the internal combustion engine, we are talking about battery electric vehicles, okay, where they do not have an internal combustion engine. And all their energy comes from the electricity grid. Okay, and they obviously, therefore, they need a much larger battery compared to the other types. On the other end of the spectrum is the hybrid electric vehicles, like the Toyota Prius, what they now call self-charging hybrids. And in fact, all the energy in the hybrid electric vehicles comes from the liquid fuel running the internal combustion engine. What electrification does is make it more efficient. I mean, basically. And in fact, basically, this is the best solution for electrification. I might as well say it now. I mean, I might say it again later. And then there are the plug-in hybrid electric vehicles where the battery size is small and you have some ability to run on electricity, maybe 60, 70, 80 kilometers or so. And when you run out of charge, the internal combustion engine will come in and take over. So it's only the battery electric vehicles like the Tesla do not have an internal combustion engine. So when we say eliminate internal combustion engines, we are talking about going to battery electric vehicles. So what is the outlook for, yes, thank you, that's the one, yeah, electrification. Now, sales of plug-in electric vehicles, that is the battery electric vehicles and the plug-in hybrid electric vehicles, are rapidly increasing. In 2019 in the UK, 73,000 roughly were sold, okay? Around 3% of the total sales of cars. Globally, it's about 2.5%. So by the end of 2019, in the UK, the battery electric vehicle stock was about 100,000. That's less than 0.3% of passenger cars, basically. And the global stock of battery electric vehicles is roughly 4 million, which is, remember the total number of vehicles is 1.2 billion, basically. And if ICEs, internal combustion engines, are to be eliminated from light-duty vehicles, the battery capacity needs to increase by a very significant size, because these battery electric vehicles at the moment are small cars, whereas the real car park of passenger car vehicles, extends from SUVs to small vehicles, basically. Okay. Now, such a massive increase in battery electric vehicles on battery size demand will be very challenging environmentally, and they'll have other economic impacts. I'll come to that now. But once again, if you remember, because the light-duty vehicles are only 45% of the total energy demand, even if you converted all of them to battery electric vehicles, you'll only address 45% of the problem. Now, this is the real important point. Okay, first of all, what is the environmental impact of battery electric vehicles? First, greenhouse gas and other pollutants. The greenhouse gas impact depends on how electricity used is generated, and the battery production is extremely energy intensive, associated with mining and everything else. And it could be up to 200 kilograms per kilowatt hour of battery capacity. So if you have a Tesla S with a 100 kilowatt hour battery, it starts with a 20-ton CO2 deficit. And this is the problem with the policies everywhere. Because all the policies, especially today's government policy, for example, here and other places in the EU, assume that battery electric vehicles are zero CO2. Even in this country, a small battery electric vehicle like Nissan Leaf would be better than the equivalent internal combustion engine. But it won't be zero. It might be 20-30% better. Okay? So the whole policy is based on a massive lie, in my opinion, basically. Because this has big implications for, all the car manufacturers, for example, are against looking at this in detail like this, because really you have to be looking at the total life cycle analysis and look at the total, the real impact of battery electric vehicles on emissions, especially CO2 emissions here. Okay? And someone once described to me that the battery electric vehicles should be called EEVs, emissions elsewhere vehicles, basically. Yeah. Yeah, because that's what you're doing. You're just shifting the emissions to somewhere else, And certainly in many parts of the world, where transport demand is growing, like India and China and rest of Asia, for example, battery electric vehicles will cause more CO2 compared to the internal combustion engine because of the energy mix and the CO2 footprint. In fact, there is a new report from Germany saying even with the German grid system, an average sized German car will be worse for CO2, taking into account the whole life cycle analysis, than a Euro 6 diesel. Okay? So it is not true that battery electric vehicles are zero emissions vehicles. Okay? And of course, the other emissions like PM, small particulates, NOx, and sulfur dioxide will also be worse in places like China, which use a lot of coal, and where the power generation is within the city limits, like in Beijing. In fact, there are several papers which show that the air quality will be worse if that is the case. But this is not the case in the UK, of course. But I'm just making the global point. And the real dirty secret, really, is the so-called human toxicity potential, though this is a bit controversial. But in general, with internal combustion engines, human toxicity potential is because of emissions from the exhaust, like NOx and hydrocarbons and particulates and so on. But with battery electric vehicles, it is mostly to do with mining of the metals needed. And at the moment, it is actually ignored because the numbers are small and all this thing happens in the Congo, the Democratic Republic of Congo or something. But as the numbers grow, because as I said, you need, if you want to convert all battery electric vehicles, all light-duty vehicles to battery electric vehicles, you have to have 300-fold increase in the numbers. these things will become important and will have to be addressed. And so the main thing we have to remember are battery electric vehicles are not green or clean. And replacing all LDVs by light-duty vehicles, battery electric vehicles, requires a huge increase in battery capacity. I mean, I said 300 times the number, but in terms of battery capacity, it's probably 1,000 times the battery capacity we have. Right. And this is an important point. Full electrification is not relevant to commercial transport. For example, a 36-ton, 500-mile range lorry like the Tesla truck will require a 1,000 kilowatt-hour battery, which will weigh at least 6.4 tons in weight, and that will take about 30% of the load-carrying capacity out of the truck, and it will cost at least 180,000 pounds. And it will require at least 12 hours of charging on a Tesla supercharger, okay? So though it is technically feasible, commercially it doesn't make any sense. And of course, there are fantasies that aviation can be run on batteries. You can do some simple calculations. A medium-range jet like the A320neo carries about 266 megawatt hours of fuel energy. A battery pack carrying that much energy would weigh 19 times the maximum takeoff weight of the aircraft. And if you wanted to charge it at 1 megawatt, the Tesla supercharger is 0.125 megawatt, okay? So 8 times faster. You will probably set fire to the battery, but that's a different matter. Even at 1 megawatt, it will require 11 days to charge, okay? So if you invented a battery which would be like 70 times better, than it is now, it will take 11 days to charge. And similarly, something like the container ship Benjamin Franklin, it will require 2 years to charge at 1 meg, and the battery will weigh 5.8 times the dead weight tonnage. So these are not possible, okay? I mean, unless there are some revolutionary changes in battery technology. Now, this is the question. Quite often, battery enthusiasts quote Moore's law for batteries. In fact, Václav Smil calls it Moore's curse, because he points out that this is not possible. I mean, in fact, there is a physics reason for this. Moore's law applies to microprocessors and electronic devices where electrons are the workhorses, essentially. Whereas in batteries, it's ions which actually occupy space. And so if you want to make a big difference, you really have to invent a new battery chemistry. And that is not on the horizon, though every day there are announcements that somebody has, improved batteries, etc. But because, remember, we are not talking about increasing by 10%, 20%. If you want to run aviation on batteries, we have to increase the battery energy density by a factor of 70. So Moore's law is not applicable. And there is also another myth, in my opinion, that autonomous cars will accelerate the spread of battery electric vehicles. But if you think about what autonomous cars would do, say, think about a New York taxi which is on call for 24 hours a day, okay? Level 5 autonomy requires an additional 1.5 to 3.75 kilowatts of extra power for electronics and sensors and so on. Plus, you could say 1 to 5 kilowatts for heating and cooling in New York, for example. So in a minimum of 2.5 kilowatts. Or 24 hours, that's 50 kilowatt hours gone. So if your battery is about 50 kilowatt hours, you won't be able to drive anywhere, basically. So it is the best solution for autonomous cars are actually hybrid electric vehicles, like the Toyota Prius, because, you don't have all these issues with them. Of course, there are other economic and other implications. Cost and availability of infrastructure, for instance. In the UK, 45% of the cars don't have access to garages. Okay, so if you want to spread this really across the board, you need a very large public charging infrastructure. About 20 million people have 20 million charging points. People have estimated this would cost anything between 30 and 80 billion pounds. So it's a question of who is going to invest in this, and of course, incentives to persuade motorists to buy them, because right now there's a huge difference in battery prices. If you go to the Nissan website, you find that Nissan Leaf, the cheapest Nissan Leaf is £26,000, and the cheapest Nissan Micra, on which the Leaf is based, is about £13,000. So when is this gap of £13,000 going to close? The enthusiasts say by 2025, and I don't see this happening in 5 years, basically. So essentially, if you're paying from your own pocket, rather than if your company buying them, why would people spend £26,000 to buy? And this is going to be the big challenge and the real test of how this thing is going to turn out. Can ordinary people actually choose? Will ordinary people actually choose to buy battery electric vehicles going forward? And if they don't, they won't spread. This has happened, for example, in China in the past, basically. They pushed for it, but they didn't buy it. And what's happening in China is the second wave of electrification, by the way. The first wave failed. Okay? So anyway, this is going to be interesting. And the cost and availability of extra electricity that is needed. It's not the amount, the energy of total electric energy we're talking about, it's the total power. In fact, in the UK National Grid published a paper, which showed that if the UK had 9 million battery electric vehicles, and this is only about 30% of the total car park, it would require an additional 8 gigawatts of power. That's 3 nuclear power stations of Hinkley Point size, basically, so these have, and not only that, it has huge implications for the distribution network, actually, and it can have basically the distribution network will have to be redesigned and rebuilt to take into account the problems created by that. I won't go into the details there. And eventually, of course, there's a problem of recycling batteries, because recycling lithium-ion batteries is extremely challenging. And I think the problems will be solved eventually, but it's not trivial, and it's going to take a lot of energy and so on, basically. And there are worries about availability of cobalt, and nickel and copper and things like that. But lithium, there's enough lithium around, basically, though the Chinese have completely cornered the lithium salts market. So there is this question about energy security in that sense. And as I mentioned already, the ethical issues associated with mining of minerals. Right. So my point is, there are tremendous barriers to rapid and unlimited growth of battery electric vehicles, and we'll start seeing them as the numbers grow, and fairly soon. And the question is, how will the numbers grow? And the numbers will grow if there is enough infrastructure, because I think what is going to stop people buying, this is my personal opinion, buying battery electric vehicles is, first of all, the initial upfront cost, and I think there is a recent paper which shows that this is the case, and what I call charging anxiety. The people used to call about range anxiety, but charging anxiety. So unless there is a good charging infrastructure, people will not buy these things, and you have to have these up in the upfront before this happens. Now, how much time do I have? Yeah. Okay. Well, let me now come to the alternative. Of petroleum, alternative to petroleum-based fuels, because as I said, 95% of transport energy comes from petroleum-based fuels. What are the possibilities? Okay, and basically, most, in fact, all credible projections I've seen say that they are not expected to take more than 10 to 20% share of the transport energy. By the way, 10 to 20% share is very large. As I said, the daily demand is 11 billion liters per day, I mean, you know, of liquid fuels. So 10% of this is 1.1 billion liters per day. So this is a large amount, but it's still only 10%, okay? Why is this? Because they all start from a low base, because this is the basic issue about all these alternatives. I mean, and this is true about the overall energy system as well. The size of the problem and the scale of the problem is extremely large, and all the alternatives start from a very low base. And there are very significant barriers, as I mentioned, for battery electric vehicles, to unlimited and rapid growth of these things. Because once they start growing beyond a certain limit, they will have huge issues to face. And they are, even in this case, they are generally relevant to light-duty vehicles. Well, I'll come to, I think there has been some talk about aviation going carbon neutral very quickly. I mean, I'll come to that in a minute in terms of these new fuels, by the way. Let me illustrate some points. Alternatives. Biofuels are very well entrenched in the transport sector, okay? Especially as ethanol. I mean, it's still, the current share of biofuels is only about 2% of the total transport energy demand, okay? Ethanol is, as I said, is primarily ethanol, and about 100 billion liters of ethanol are produced per day. I mean, this is not 2018 figures. 2019 might be slightly higher. And there are many drivers for, biofuels. I mean, in most countries, it is import substitution, self-reliance, security of supply, and so on. India spent a lot of money and effort trying to reduce import of oil by going to biofuels. Use of agricultural surpluses, and in some cases they might have greenhouse gas benefits, okay, depends on assumptions. However, most environmentalists are against biofuels now, mainly because of the food versus fuel argument for land, okay? And they also have higher costs per unit of energy. That's a different matter. And deforestation, water, fertilizer use, along with the land issue, is a very big barrier for unlimited growth of biofuels. However, these, in some countries, if they can get it done, they will get it done in spite of this, because the main driver is import substitution. I mean, they don't want to import Saudi oil, basically. Yeah. And there was a lot of fuss and a lot of hope about so-called second-generation biofuels because of this first issue, for availability of food versus fuel. Basically, you use waste, to make, bio-waste to make, from crops to make biofuels. And it has not gone well. For example, the actual production in the US in 2015 was 2.2 million gallons of gasoline equivalent. The original requirement by the law passed in Congress for RFS renewable fuels requirement was 3 billion gallons, because the technology has not developed. Doesn't mean it will not. I mean, and maybe there will be some new technology based on genetic modification and so on. And in fact, ExxonMobil have spent a lot of money on going down this route. There might be solutions to this in the future, but at the moment there are no solutions. Natural gas is another very good example. In fact, there's great faith in an increasing share of natural gas in the transport industry. Right now, it's about 1% of total demand, okay? But it's expected to go to about 5% because especially because of cheap natural gas, because of fracking and so on. And it has some possibilities in marine and railway, marine especially, and heavy-duty goods vehicles and so on. But the main barrier is still infrastructure, because you have to move around natural gas. And the initial cost is high, and the driving range is low, etc. But the outlook is there is renewed interest, and some people expect it to go to 5% from the current 1%. So we are coming from 95% transport energy from petroleum-based fuels to more towards 85-90% now with things like this. There are other alternatives, liquid petroleum gas, dimethyl ether, and methanol, which have niche applications at the moment. And I think of all these, methanol is the most interesting. There is a lot of interest in methanol because it can be made from very low quality coal. And there is a lot of interest in India, and China is already using a lot of methanol, for example. So methanol also has some good combustion properties, though there are some bad properties as well. That's a different matter. But essentially, I could say use of such fuels makes sense somewhere, sometime. And they will continue to be used as niche fuels, except that, in my opinion, methanol is a very interesting future fuel which could increase its usage. Here is an interesting thing. Hydrogen is a big favorite now, and it has been a favorite for a long time. Under the Bush administration, several $1 billion were spent on hydrogen research, basically. But the problem with hydrogen is, like electricity, it's an energy carrier. It has to be manufactured, and it's very energy intensive to make it. And production can be made from all kinds of things. It can be made from almost anything, you can say, but then the question arises, but it has to be, if you were concerned about CO2, it has to be made from CO2-free energy. So the question is, if you want to make it, if you have enough CO2-free primary energy, why make it into, convert it to hydrogen? Why can't you use electricity directly? These are the questions. In fact, Elon Musk keeps asking this question every time, by the way. And the big issue about hydrogen is the storage and transport issue. Compression, it has to be compressed or liquefied to carry enough energy on board. For transport, I'm talking about. It can be used for other applications, okay? But that will lose 25 to 40% of the energy. And the infrastructure required is extremely expensive. During the Bush administration, there are a lot of US government institutions studied this, and the costs are 15 times for the cost of liquid hydrocarbons, and 4 times the cost of natural gas for distribution network. So at the moment, it's not a viable transport fuel for transportation, in my opinion. And it will require huge amounts of investments in renewable energy before it becomes, comes into a serious contention. So even in 2040, I said that roughly 90%, 85 to 90% of transport energy will come from petroleum-based fuels. So improvement of such systems is imperative to ensure the sustainability of transport. Let me explain this. So when we say battery electric vehicles are not zero CO2, say you're saving, say, 20% of CO2, say, okay? And they're only about 0.3% of the total car park. So if you improve the efficiency of the 99.7% of the other car park, you could make a much bigger impact on CO2 emissions at the moment. Okay? So how do I see this? I see this as there are 3 stages to this. In the first stage, conventional engines, the engines that we know now, using fuels that we know now, improve their efficiency and fuel, reduce their fuel consumption. And there is tremendous scope for this. I'll just explain some of the points here. Through better combustion, better control, better after treatment, coupled with partial electrification, like with hybrid electric vehicles, to make huge impacts in the efficiency of current engines. And in stage 2, we can think of developing new fuel and engine systems, okay, which allows greater scope. I'll come to that in a minute. And in the final stage, in the long term, as the overall energy system is decarbonized and battery technology develops a little bit better, there will be increasing role for battery electric vehicles as well as for hydrogen. And in this context, I think I have to mention so-called electrofuels. I think there is a lot of thought that electrofuels are basically use renewable electricity and make liquid fuels using CO2 and hydrogen to make liquid fuels. Okay, and this is the kind of thing that the aviation industry is talking about, because you can have zero CO2. But the energy calculation for this is extremely bad, because it takes a lot of energy to make these liquid fuels. In the last few days, I've been engaged in some calculations with some friends of mine at Imperial College and so on. And if you, to cut a long story short, if you want to convert all of aviation globally to electrofuels, essentially the world will have to build an equivalent power system of about 400 plus nuclear power stations of 3 gigawatts, or more than 1 million 3 megawatt wind turbines. Okay, so it is not trivial, and it's not going to happen in most countries, and even in fact it is not going to happen even in Europe, I think, because the costs of it are going to be very high. So when the aviation industry say they're going to go to zero carbon, I mean, this is the same argument for hydrogen as well. I mean, hydrogen is a bit better than electric fuels, because the energy conversion to hydrogen is better. But it's basically it's the same problem. Okay, now what is the scope for improving the internal combustion engines with existing fuels? To cut a long story short, if you combine all the things with combustion improvements, control improvements, partial electrification, possible lightweighting of vehicles, vehicle downsizing, and so on, you can reduce the fuel consumption by 50%, okay, with existing technology. But it requires you to go to lighter cars and smaller cars and better combustion systems. The question is, what about the emissions? Because this is a big issue with the internal combustion emissions. With particle filters, there are zero particles. In fact, Euro 6 diesels in many, many urban centers will have cleaner exhaust than intake. This is true. I mean, in fact, this has been done. I mean, and this is true about gasoline engines as well. Actually, GM has demonstrated this to the US EPA in Los Angeles, for example. In Los Angeles freeways, the hydrocarbons emissions are lower at the exhaust than in the intake. It will be certainly true in a place like Delhi, for example. So there are again more scope with doing all this with so-called low carbon fuels. I mean, some of the things that I mentioned, but all these things have to be done only if they make sense. And it is extremely important that all these alternatives are assessed honestly on a proper life cycle basis. Otherwise, we'll end up with what has happened with BEV, battery electric vehicles, assuming that they're zero CO2 emission vehicles. Now, let me just quickly mention some examples of fuel engine system development in a few more slides. One of the very interesting areas is the so-called gasoline compression ignition. Okay? The problem with diesel engines is that they have high NOx and particulates. The reason this is so is because they use diesel fuels. The diesel engine is the right combustion system, but for historical reasons, it's been using the wrong fuel. And in fact, the reason this happens is that diesel fuel ignites very, very quickly because that's how it's intended to do. And therefore, before it has a chance to mix with oxygen in the cylinder, it starts burning, and that's what causes these emissions, basically. But if you use gasoline-type fuels, especially low-octane, gasoline-type fuels, these are more resistant to auto-ignition, so they'll have more time to mix before they start burning. And therefore, you can reduce the amount of emission, NOx and particulates produced inside the cylinder very, very significantly. You can go to zero, in fact. And there has been a tremendous amount of research done on this recently, in the past 6 or 7 years. I demonstrated this about 2006 and 2007. And Saudi Aramco, by the way, are putting a lot of money into this, developing this technology. So this is, by the way, this is an example. Remember, I mentioned right at the outset that we might have an excess of low-octane gasoline fuels available. And these are exactly the kind of fuels that can be used here. So it will solve a lot of problems together. And there are other technologies also which we can use low-octane gasoline technology. So the summary then, I can leave this like this and go to questions because I've said everything I want to say.